Here's a shortened version of a talk I gave last week at the SEG IQ Earth Forum in Avon, Colorado. I was invited to speak on the use of seismic techniques for studying geothermal reservoirs. Before I dive in, I want to ask this question, because it didn't come up at the forum, but I think it should have. Interpretation's become a jargon word, and we haven't spent a lot of time describing what that process looks like, and we haven't spent a lot of time talking about what it feels like. Some say that seismic interpretation means looking at wiggles and picking horizons and faults on a workstation. In this talk, I demonstrate a thorough reservoir evaluation without picking a single horizon or fault. Maybe this is possible because I haven't picked any horizons or faults, and I think it's where more and more interpretation is heading. Depend less on static map making and more on algorithms that allow the testing of multiple hypotheses. Here are some salient features of the regional setting. The project lies in the Salton Trough, which is the northern extension of the Gulf of California rift, shown here in the top right. The project is at the northwestern end of the Mesquite Basin, a small pull-apart basin above an active rift. The rifting is at a step-over system from the San Andreas Fault to the Imperial Fault. It's a major strike-slip zone, and there's active sedimentation from the Chocolate Mountains to the north. Here's the stratigraphic column. It's rapidly subsiding, actively being pulled apart. Overall, there is a marine to alluvial regression. This schematic is the first step in building a field-specific model for the low-grade metamorphism, which will eventually help predict reservoir quality. The basic idea is that there are these paragenetic zones driven by temperature, and these zones have different geomechanical properties. The propylitic zone is the most favorable for hydrothermal energy systems. When hot, hypersaline fluids circulate and cool, they precipitate out cements into the host rock, especially in the most porous sandstones. We call this the cap rock, and we show it here in blue, and it has this patchy, here and there look to it. And you can see how structurally complex it is. Conceptually speaking, this geothermal system can be separated out into two parts: the antecedent geology, which is something we could target using standard seismic interpretation methods. And then there's the subsequent geology, with the hydrothermal metamorphism and diagenesis. A conventional seismic interpretation, picking horizons and faults, would not only be difficult in this area, but it may in fact tell us very little about the system components we're interested in. Here's what one well looks like in a standard VPVS acoustic impedance crossplot. The overall depositional trend is offset or perturbed when there is this diagenesis. The cementation effect is a significant deflection away from the trend. In our early viewing of the data, we recognized at least 4 sets of seismic reflection patterns, and we wholeheartedly call them seismic facies. We think for everybody doing interpretation, it's at least a little bit novel to say, what are my seismic facies, before you even try to pick reflections. We form an impression of an Earth model before we even touch it with a digitizer, with a paintbrush, or pencil crayon. Traditional horizon picking means picking events or reflections. Now, picking the top of this metamorpho zone is like picking a phase boundary, or a facies boundary. It's not easy to do on a workstation, there's nothing automatic about it, and it's far too subjective. Nonetheless, in our initial work, we picked the top of this low semblance zone. We call it the top of the dead zone, for lack of a better word, and we mapped it and examined it for additional attribute anomalies. We noticed that amplitude, semblance, and energy, all in their own graphical way, delineate different properties of the geothermal system. Amplitude shows the stratigraphy and the layering. Similarity shows discontinuities and this metamorpho zone. And the energy attribute gives these patchy blobs of high energy, which we think is this cemented up rigid sandstone that's become more acoustically heterogeneous. And when we add everything together, we have a basis for comparison with the diagenetic model. We stack these layers up to understand where the most favorable zones might be. Adding isotherms from well data looks like a low resolution sampling of the geothermal system. I wouldn't go so far to say that we can image temperature using seismic. However, temperature is an alibi for all these other geomechanical effects. This exercise of exploring several post-stack seismic attributes and making layers is one that allows us to describe many features that are unmappable. The problem, however, is that I drew these layers painstakingly in a graphics editor. It took me several tries, several days. It's too subjective. But we can do more with these attributes. We can be more systematic with them, less artistic. We want to move beyond the cartoon cross-section and get this kind of detail over the entire 3D volume. So recall that we've arrived at 4 main facies here by using 3 attributes. We can pose this as a data clustering problem. Any ensemble of attributes, whether it's the 3 that I've just shown or 7 of your favorite pre-stack attributes or spectral decomposition attributes, all of them are co-located for each point in space at each pixel. As such, any number of attribute dimensions can be used to uniquely classify each point in space. Now, how many attributes you should use or how many classes are there, there's no general answer to this, and it just depends on how your data is clustered. The concentric ellipses around each cluster denote this notion that each point can be assigned a probability of belonging to each cluster or each facies. The points on the periphery of the cluster are assigned a lower probability. The points near the center of mass are assigned a higher probability. Here's an example using the 3 attributes I just shown, amplitude, similarity, and energy. We cluster them together into 4 cluster groups, and we get the colored classes shown on the right. Now, if I simply assign a new color so that it matches how I've drawn my cartoon, here's the comparison we can make. To help, I've made the gray facies on the right semi-transparent to show the amplitude data underneath. And I've overlain the drawn fault zones for an easier comparison. So the first shot at it seems to be a decent representation of the system. Certainly not perfect. It seems like we're overestimating some of the cap rock we think is there, and the near surface is garbage. We also see that there's some problems with the low fold regions at the edges of the survey, but it's not too bad. Matt and I became fascinated by the complexity of the objects and shapes suggested by the diagenetic model, and we wanted to do more to try to elucidate them from the data set. So we used some statistical properties of patterned images called Haralek textures. What we're doing here is basically saying, give me 4 numbers at each pixel or at each sample in the data set that describes the texture in the small neighborhood around every pixel. These textures now become 4 more attributes or 4 more dimensions to the clustering problem. Now there's plenty of features that we can compare here, and with the faults overlain, you can slide your eyes back and forth from the cartoon to the classification and make your own comparison. You can see it aligns quite well, and you can see we're actually capturing more detail in the facies classification. We could do some other things to this, like maybe add a fold volume to filter out the near surface part that is struggling and these low fold regions on the edges. But the idea behind the rightmost image is that it's not just a cross-section that we compare to our geoseismic line. It's actually a full 3D volume that we can explore and slice and dice however we want. So here's a time slice at 1,000 milliseconds. And I think this volumetric mindset is the mindset we need to embrace when we do interpretation. Even things that are incredibly irregular and complex shapes have a full expression. So we're going to be processing some of the seismic data, looking at it for fracture attributes, looking at more of the azimuthal response of the seismic data. We've got more work to do here, but this is a pretty good start, we think, in sort of providing more information in what is a very difficult to map area. I say stop yourself from making surfaces from rich 3D data. If you're picking reflection events, at least use them as boundaries to probe in between with attributes. And if you're using this word interpretation, really describe what you're actually doing. Whenever possible, try to make your interpretive work into an algorithm. Get it out of your head, get that instinct and that gut feel that you have into an algorithm and share it with people. I think you'll find that there's new creative challenges with doing this, and you'll be a lot more useful for people. Consider quantitative clustering and classification schemes. And if you like to try out some of this stuff, you can go to GitHub. I'd be happy to help you with it. So that's all I wanted to say. I hope you had fun listening to this talk.